Welcome to qnawire.
We begin this question by using Newton's second law to calculate the acceleration of the objects. For that, we can do the following. So there is a small trick that we can use in these situations, which is the following. It's a system composed by three objects, but all of these objects move together, so they move with the same acceleration. Then, when we are interested in calculating the acceleration of the system, we can choose a reference frame and treat the system as a whole, like this. Let me choose my reference frame as being this weird reference frame. Okay, in this reference frame, I will consider the whole system. Therefore, the net force acting in the whole system is given by the mass of the whole system, which is m1 plus m2 plus m3 times the acceleration of the whole system. Now, what is the net force that is acting on the whole system in the direction of my axis? There are the following forces. Weight number 1, tension, tension again, tension prime, weight number 3, and a frictional force that points to the left. It's important to mention that I know it's pointing to the left because this block is heavier than this block. So the system, if moves, is moving to the right and the tension is pointing to the left. Then, knowing this information, we can write the net force as follows. Minus W1, because it goes to the negative direction, plus T, because this tension points to the positive direction, minus T, because that one points to the negative direction, plus T prime, minus T prime, plus W3, and then we have the frictional force minus FF, and this is the total mass of the system, M1 plus M2 plus M3 times A. Then, notice that there are several cancellations because of the pairs of action and reaction of tensions. So there is a simplification here and a simplification here, and we are left with the following. W3 minus W1 minus the frictional force is equals to the full mass of the system, M1 plus M2 plus M3 times A. Then remember that we can write the weight force as mass times acceleration of gravity. So M3 times G minus M1 times G minus the frictional force. The system is moving, so the frictional force is given by the normal times the kinetic frictional coefficient. So we have minus kinetic frictional coefficient times the normal force being equals to M1 plus M2 plus M3 times A. Then you can see from the problem that the normal force is clearly equal to the weight number 2. Therefore, M3 times G minus M1 times G minus mu K times the weight number 2, which is M2 times G, is equals to M1 plus M2 plus M3 times A. Then we can factor G on the left-hand side to get M3 minus M1 minus mu K times M2 times G is equals to the total mass M1 plus M2 plus M3 times the acceleration. Then you can send this term to the other side to get that the acceleration is G times M3 minus M1 minus mu K times M2 divided by M1 plus M2 plus M3. Then we can plug in the values to get 9.8 times 25 minus 10 minus 0.1 times 80 divided by 25 plus 10 plus 80. This results in an acceleration of approximately 0.60 meters per second squared. Now, before solving the next item, I have to organize my board. Okay, In the second item, we have to calculate what are the tensions in each of the strings. For that, we have to apply Newton's second law to this and to these blocks separately. Beginning by block number 1, we get the following. Still using the same reference frame, Newton's second law tells us that the net force acting on that block is equals to its mass times its acceleration. The net force acting on block number 1 is plus the tension that points to the positive direction minus the weight that points to the negative direction. Then, tension minus weight 1 is m1 times a, and that's it. Now we solve for the tension to get m1 times a plus the weight number 1, which is m1 times g. Therefore, the tension is given by m1 times a plus g. Plugging in the values that are given by the problem, we have 10 times the acceleration that we had calculated plus 9.8. This results in a tension of 104 newtons. So this is the tension in this string, the string on the left. Now, for the tension on the string of the right, we have to apply Newton's second law to block number 3. By doing that, we get the following. The net force acting on that block is equals to its mass times its acceleration. Then, notice that there are two forces acting on this block, the tension force that points to the negative direction and the weight force that points to the positive direction. Then, weight number 3 minus the tension is equals to m3 times a. Then I solve this equation for the tension by sending this term to the other side and this term to the other side. So the tension is given by the weight number 3 minus m3 times a. Plugging in the values that were given by the problem, we have the weight number 3, which is 25 times 9.8 minus 25 times the acceleration of 0.60. Then, this results in a tension of 230 newtons. So this is the tension on the string of the right.